Okay, so in today's lecture, we're going to start to talk about the module 3. Wait. Yeah, so like today we're going to talk about module 3, neural network. So in 592, we are using in 592, we are focused on the theory of the neural network. That means we are actually are going to implement everything from scratch with NumPy and SciPy. So in 593, when we encounter much more complicated so neural networks, it will be much more convenient or easier to use PyTorch. So you can work on much more complicated tasks. But in 592, in machine learning, the point everything is we need to understand what is going on. So that's why we are going to implement and all these neural networks and from scratches. So let's review and let's review on the material that we already had for the multi-class. So classification problems. Okay, so and this is basically the same framework that we're going to work with on neural networks. So basically, it's the given data is the training data. So we have a D equal to X of I, Y of I, Y is the label. And this is your input feature. In R big D, and this is your label. Right, so in this case, let's assume this is K-class classification. So that means all these Yi is in 1, 2, 2DK for K-class classifications. The goal here is we actually want to learn a vector value. Function with some tunable parameters, with some parameters. Like what does that function look like? It basically looks like this of theta. This theta takes input of R big D and actually output of 0, 1 to the K. So basically is a vectors of like of size of K. But each component is between 0 and 1s. So in particular, its C's component, which is the C's component of output, is actually the predict probabilities. You can like actually treat as and predict probabilities of the Y. It's Y equal to C given for the X and theta. Right, so this is basically the predict probability of this input data. Xi belongs to the class of C. So this is, and each output has this probability meanings. And so of course the summation of all possible C from 1 to decay of each component becomes 1. So that's why F here is actually, you can think about, is a probability vector. Right. And also how we make the prediction is the prediction is, the corresponding, and so I make prediction to the class of C such that it's basically, this is argue max of my FC. So let's just not to call it C here. So this is how we do the prediction. So this and X belongs to the following cluster, which maximize the predict probabilities. So this is belongs to, and then so if this is let's call it and a little k here. So then we say that input data X belongs to C. Okay. All right. So and then the point is, the whole training point is we want to tune that tune the theta such that all the argue max of C of FC of X of I theta equal to Fi for all I equal to 1 to the n. So of course we want to make sure all my predictions to matches the ground truth as much as possible. And why you tune these parameters. Okay. And of course we talk about and the logistic regression. So we actually did that with and the logistic regression. So for logistic regression, this F function is a composition of the linear plus the softmax. So first we apply a linear function, then we apply the softmax function such that the output becomes a probabilities. So in terms of the linear function right here, this z of x is actually w times x plus b in the RK. So this z here, it's called pre-activation vectors. So this w here is actually in R k times d. So it's my, that will be my weight matrix. And B here, so this is my weight matrix. And my B here is in R k, it's my bias. But here we so what we usually do is and we basically put this and a bias out of this weight matrix, and just And that's like slightly different from the logistic regression that we had. And before previously, we just put and this bias or intercept into the features, then you adding like column ones. But here I'm going to move this bias out just to be consistent with the neural networks later on we want to talk about. So this is slightly, and a slight difference is here. So this is the something called linear layer or linear and the linear function part. So the second thing is the softmax. So I mean, it's basically we're going to output of that becomes, I mean, it becomes a vector is I'm going to apply the softmax on this pre-activation vector Z right here. So I mean, if we combine both of that, this is softmax of W times X plus B. All right, so and of course we can and write everything explicitly. If we write everything explicitly, so this is actually becomes the following. So right here, I mean, it's actually Z, so this becomes softmax of W1 times X plus B, so which is Z of 1 to WK X plus, I mean, this is B1 plus BK. So, and this W1 here is, and I mean, the first row and the WK is the last row. So basically, WJ is jth row of W. So this actually equal to exponential of W1x plus B1 divided by summation of J. So basically summation of each component. Bj. So this will be, so basically normalize this component and everything into a probability. So we take, so basically we take exponential, then like normalize into probabilities. So this is basically what we do on, and for the softmax. This is WK X plus BK. I think this is capital K divided by summation of J X plus BJ. All right. Okay, so this right here, and we have a K component. Each component is between 0 and 1. And this is giving you a probability vector. So this actually satisfies our requirement of these three terms right here. So we have this, and the requirement, this F is to be a probability vector. I mean, so after we apply softmax, this automatically becomes a probability vector. We can make predictions that that my input data belongs to the class C, which that class has to maximize this prop and the probability component of F. So we haven't talked about how we tune and train this part yet. But nevertheless, I mean, this model actually fits to this framework. And also, and we have mentioned this W right here is, and B here will be my parameters, right? So this is the parameter we actually want to learn. So the theta here is my W and B. Okay, so now the goal is we want to find out the optimal theta that actually minimize the training loss. So the goal in like logistic regression is to minimize and some loss functions. So here what we use is the cross entropy loss. So I want to remind you. So cross entropy loss is defined as follows. If you have a given, basically given a training sample, x of I with our model and prediction give you a probability vector of f hat x of I and theta, and my yi is either the value from 1 to the k, then the cross entropy loss says this loss is actually equal to f of x of I and so this is my predictions, and this is my ground truth of y of I. So this is not fully consistent because my f is actually a vector, my yi is a label. This is being said, this is equal to minus logarithm of f yi, which is corresponding label, and a component of x I and theta. So we know this term is between 0 and 1. After we take the logarithm and put a minus sign, this is always bigger or equal than 0. This is only equal to 0 if this probability component is precisely equal to 1. That means and the probability that to make prediction and on like y and yi component and to be 1, then of course and everything else should have the probability 0. So and of course we can make the perfect predictions. So why this is like that is because and I want to remind you and previously what we have is so, and the reason it's the same like this is we can make this yi to turn this into one-hot encoding becomes y vector of I. So this y and y vector of I is actually just, I mean it's one-hot vectors of yi, but only at yi component to be 1 and everything else just being 0. Right, so this is one-hot encoding of my label. So then the like cross and the high and hypothetically the cross entropy loss becomes summation of j of y and yj of I and the logarithm of j fj of x of I then theta. So this is basically says because and the only thing that actually contribute is when j equal to and yi. So I mean this is basically equal to and the logarithm of f for yi of x of I. And yeah. So this is because and when j equal to yi, then fj equal to 1. When j is not equal to yi, then this then the jth component is actually equal to 0. All right, so I mean, that's how we get this in a simplified form for this cross entropy loss. So this is what we're going to do for the cross entropy loss. So this is to ensure this, I mean, this quantity right here is, and which is my predict probability for the class of yi, is as large as possible. And of course, the largest that we can get is close to 1. So this is, I want to ensure this predict probability as large as possible. Okay, so this is basically how you treat everything. And of course, that's cross entropy for just one data of xi and yi. And we actually need to have the whole and the total training loss. So basically this L of theta and the D is equal to, we are going to sum of all each individual cross entropy loss. Sum of I from 1 to the n logarithm of f yi x of I and the theta. So we sum them together, and I have a -1 over n. So this is just take the average of this. So this is basically the cross entropy loss on the full training set. Okay, and of course you can add some penalty if you need it. Sometimes we might add some penalty of lambda of and usually we put the Frobenius norm here, and Frobenius norm of W right here, or maybe you can put 2 norm if you want. Okay, so and this is penalty term is optional. So if we add penalty, so the whole point is trying to reduce overfittings here. All right, so then at the end, use SGD or mini batch gradient descent to minimize the training loss. Right, so this is the whole story underneath of this. And I want to remind you this picture that we had before. Right here, I want to remind you this picture. Right, so and I believe you have seen this picture before. So and if you are giving this MNIST data set, the first thing I'm going to do is you're going to reshape into a row vector. Then this becomes 784, the vector here. So the first thing that you do is we had W times X plus B, and the W is my weight matrix, B is my bias matrix. So we do this linear and the linear transformation. This Z becomes pre-activation vector, which has a 9 of that from 0 to 9. Then we apply this and the softmax function right here, which is formulated as this follows. Basically, take exponential of Z component that we normalize into the probability. You can see this will be the output of my my value after softmax. This will be my predicted probability. The key of this is if we sum them up, it will becomes 1. But if we look closely, how we make the prediction is to find out the component that actually maximize the predict probabilities. In this case, it will be Z3. So we will make the prediction for this image to be 3, right? But also you can have a look at what is the second most, which is 8 here. So I mean, I guess the reason is like this being predicted to be A is, and this is not too far away from A if we have this like stroke right here. But of course, the probability to be predict on to 9 or like 0, this will be significantly lower. So this just give you some like a good idea how this and the logistic regressions make the predictions and how likely and being predict on other like digits other than 3s. And of course, the point of everything is we want to tune in this W and B to ensure this output vectors always and predict and to make the Z3 component to be highest. So that would be our goals. But of course, if we change another images, the corresponding like Z and a component will be and highest if like as much as possible. So this is the whole point. So if we actually look everything right here, so this is a like diagram that we have. If we have a like binary, like and so logistic regression is we have input of this like information here. Say here, right here, we have a, like only 4 dimensions. But of course, for the MNIST, that would be 784 like any dimensions. So we just do so basically a linear function passing this linear function right here. Then we ensemble this like output. Then we apply this sigmoid and sigmoid functions and to make predictions and for 0 and 1s, and that will be my binary and logistic regressions. On the other hand, if we have a multi-class logistic regressions, then the output will be like more than 1, which in this case it will be 3 of that. Then we apply the softmax and for this like pre-activation vector, and then the output will be predict probabilities for that. So the key here is to ensure like an all 3 component and predict probabilities sum to be 1. So this is the difference between the binary and the logistic regression and the multi-class and the logistic and regression. For the binary class and the binary one, we only have a 1 and the 1 output because we only have a 0 and 1, and the only thing that we need to do is to predict the probability of 1s, because the other one will be just 1 subtract to this. So we don't actually need to have a 2 classes here. I'm actually need a 1 class. That will be sufficient, right? So this is actually just have a 1 dimensions and problems. But of course, if you have a multiple classes, more than 2, then you actually have to have more than like and 1 dimensions to work with. In this case, it will be 3 and the dimensions to work with. All right, so that's a diagram that will be helpful for you to understand this logistic regression. Okay, so as you can see right here, so I mean basically in the logistic regressions, you have all these like and input, which in the MNIST data set that will be 784. Then we just and apply to and to have like bunch of an output, and this output will just be the probability here. Okay, so you can think about this way. But what you can do is the other way is so let me just show you this screen one more time. So this is basically a very simple version of neural network. It's 1 layer hidden neural network. So basically if we get rid of this like hidden layer, we only have like input and output. This is nothing but so logistic regression, as you can see right here, we have a input and output. And this is my input and this is my output. And of course, inside it we had composition of the linear and the softmax. Right here, in addition of the input and output, we have something on the hidden layers. So this will be my hidden layers. So each circle right here, you can consider as a neuron here. And you can think about this is like input features, and this is also the and hidden layer, and this is my output layers. So let me just draw these things, so a little bit carefully. So if we have this x1, x2, x3, x4, say we have a 4-dimension, we have hidden layer that is 3 of this. So that means everything is connected. We consider fully connected situation. Okay, so that means this will give you Z1, Z2, and Z3. And then say my output is 2. So that will be fully connected as well. Okay, so the output will be some like 0.4 and a 0.6, something like that. So right here, so this is called input layer. Here we have, and like this x1 to xd is from the feature input feature x in RD. So in here we have 4 different neurons. And right here, this is a new thing. So this is the hidden neuron and hidden neuron layers. So you don't actually see it at all, which basically process the input from the previous layer and output the result for the next layers. So in this cases, we have 4 and hidden neurons. So in this cases, I'm going to call this as like, and I call this A and Z, which is, and this, so input will be something called W1 of the x-axis coming from the input layer plus B1, right? So this, I'm going to call this as a Z of X, right? So Z here is also a vector. And again, we consider this as being a pre-activation vector. Then in this cases, our W1 is in R H times. In this case, my and my H is equal to 3. So this is H times D, and B1 is also in RH. So this is pre-activation vector. Then I'm going to apply the activation function element-wise. So I'm going to apply A of X is G of ZX. All right, so, and this whole thing is applied element-wise. So element-wise activation functions. So basically this AJ of X is equal to G of CJ. Right, so this and this function is applied and only element-wise. Oh, what happened here? Oh yeah, good. All right. So and also this layer and the linear, and this right here is called the linear layer as well. So this right here is called linear layer because this is a linear function right here. And because my W here is and consider most likely to be like an almost everywhere non-zero. So this is also considered a dense and a dense linear layer. All right, so and this is the and from input layer to hidden neuron layers. Then this and the last one will be called output layers. Right, so this is an output layer. In this case, we only have 2 neurons. So like from hidden neurons to output layers, and this is basically we are going to output something like and what we already have, like so logistic regressions. So we're going to output this x and theta. This will be softmax of W2 of AX plus B2. Okay, so, and I want to remind you my AX is defined right here. So we can write everything all together. This is become softmax of W2 G of W1 X plus B1 plus B2 altogether. And then the output will becomes the value between 0 and 1 and we have a K component. So in this cases, my W2 here is actually has a dimension of K by H. And also this, I mean, so and you already know what is softmax. I don't need to like repeat this. And my B2 is in RK. So so this is also, and this also, I mean, is a like second linear layer here. So and this is my linear layer again. So basically, we apply and the linear layer. Then after that, we apply a softmax functions. So basically, if we have a one hidden neuron layers, so what we do is we first apply a linear layer, then apply one activation function G. Then we apply the second linear layer, then we apply the softmax functions. At the end, we will like output the probability. And of course, there are a bunch of choices of G that we can choose. Well, and I'm going to talk about this a little bit later. But this, I mean, the key here, this G is always applied element-wise. So, and we are not doing fancy matrix multiplications on this activation, just and directly apply that element-wise. So, and everything can be done parallel and very efficiently. And then in this case, is my theta right here is not only the W2 and the B2 like what we had in the logistic regression. It's, I mean, instead we have W1 and B1 and the W2, then B2 will be our model and parameters for the linear layers. So we only need to tune the parameter for the linear layers. We don't actually need to tune for this activation function because activation function is all pre-given here. And also, I mean, at the end, the total like cross entropy loss. So we can use the same idea from like logistic regression. We have a cross entropy loss that is -1 over n, and the summation I from 1 to the n and the logarithm f of yi and x of I tan theta. Okay, so basically, and we want to make sure this like and for the input data of x of I want the yi's component to be and yi component of my predict probability as large as possible. So this is the fundamental goal here. And also the reason that we use cross entropy loss, it actually has something to do with MLE estimator. I mean, I want you to go back to look back to this and the logistic regressions. Why we want to choose and a cross entropy. The reason is, and it's basically I mean, if we want to minimize this cross entropy loss, it's almost equivalent to say we're trying to maximize the log likelihood functions. All right, and I hope this is quite clear. So basically, this is artificial neural network. So this whole artificial neural network is basically compositions of many functions. And you can think about each neuron here is actually a function. You will accept, for example, this U1, it will accept input come from all neurons from the previous layer, and also output for the next layer. So these will be your input to the Z1, and the Z1 also output to and for the next layers. And the whole point is neuron will be activated if they have a high value. If they have a low value, for example, close to 0, then they will not be activated. Okay, so and sometimes we can change even the last layer as well. So let me just show and show you a little bit right here. And right here, we assume the last layer to be softmax. But sometimes it won't be a very good idea. But yes, it's because the softmax is not element-wise. If this, max is not element-wise, it will be relatively more expensive when we actually implement this. And one thing that we can do is we can make one modification here. Is we can change the last layer softmax to sigmoid, right? So that means my output is no longer to be a vector, so probability vector. So this is just a simple sigmoid of my W2 of AX plus B2 here. That is possible as well. I mean, there's no kind of restriction. It has to be used and the softmax here. And you can use sigmoid if you need it. So this is a sigmoid functions. Of course, but if we're using like sigmoid functions, then the key here is we cannot use cross entropy loss anymore. Because this sigmoid value right here is not necessary to be always normalized. So I mean, could be some value could be like super and a large, some value could be super small. That is totally possible. So I mean, necessary to be like normalized to be one that is totally, even possible, all the values that we got after this sigmoid to be all very close to 1. So like, and it is nothing, about like, and the normalization. So it won't be a good idea just to maximize one component here, because maximizing one component in this situation may not be properly and represent for this and represent for this the output, because the output could is no longer normalized. So if we're using, if we want to use sigmoid function, then we need to change the loss functions to like log loss. So this is very important. You can't just use the same loss function here. So the loss and the log loss given as follows. So we still have 1 over n of summation I from 1 to the n of log loss of f yi x of I, then theta. So this is still the like yi component. So we want to still like maximize the yi component, but also I want to minimize the other component that is not equal to yi. J is not equal to yi. I want to minimize it. Such that I want to ensure the like yi components is actually truly maximized across all component right here. So right here, we want to maximize the yi component. Right here, we are trying to minimize those component that is not yi's. Right, so this is log and the log loss right here. And of course, we can use the same one-hot encoding trick, one-hot vector of yi is actually equal to, I'm going to using the same idea, EYI. So this is, this actually is a vector right here. So we can rewrite everything in terms of and vector like formulations. So this is 1 over n, summation I from 1 to the n, summation j from 1 to the k, yj I. So this is the ith component of this one-hot encoding times of log of fj x of I of theta plus 1 minus yj of I log of 1 minus fj x of I theta. Okay, so that means, if it is 1, which is corresponding to j equal to yi, so we will take up and take on this term. If it is 0, then we will take this term. So this is basically, it's like generalization to this multi-class cases. I think we had a similar version that we have in the binary cases. So this is actually the log loss. So, and this is also commonly asked questions in like data science interviews. What is log loss? Can you write it up? Right. And many people actually got stuck here. So this is something that is and very important. Of course, we can, use square loss if we need it. Square loss is also possible. So that means we can take the theta and the d, 1 over 2n, basically summation I from 1 to the n. We take the square root of 2 norm of the output f, subtract y. This is actually a vector now, and a 1-hot encoding of the y, I, at norm of 2 square. So this is totally possible. We can use all these square laws if needed. All right. Okay, so this is basically like some of the math that I'm actually needed. If we actually look at this and whole summary here, it's basically the whole thing and a neural network between each 2 layers. It has like 2 important components. The first important component is the dense linear layer, right? So this is basically linear mapping. It's like parameterized by the weight W and the bias B. And both input and output will be vectors, right? If the input is an images, you are going to flatten that, and such that to ensure that and your input has to be a vector right here. So basically, each of output of Zj, which is the jth component of the pre-activation vector Z, is the weighted average of X plus and a bias term. So this is Wj, which is the weight, plus like Bj here. So Wj is actually the jth row of W. So you actually have, and it could have a different weight for each like component of J. So here what we call this dense is because all my the connections between and the previous layer and the current layer, it has a full connections. So this means and for the input and output component, and we always has at least so we always have a connections between any 2 neurons from the input layer and to the output layers, and to the previous layer to the current layers. So that's why this is called dense, and to be reflected in terms of parameter, that means all of my value for my W will be non-zero. If it is 0, that means one of the connection is missing. But if if it is non-zero, so that means we always have some kind of connections between between ith neuron to the jth and from ith previous layer neuron to the jth current neurons. So that's why this is also called fully connected layers. There are some connections to the biological neurons. You can think about this is actually a neuron right here. It received input from the previous neighboring neurons, and we have certain weight and trying to take some ensemble with that. And after that, we're going to take some an activation functions. So this is basically the activation functions, and called F right here. So there are multiple activation functions that we can apply. So almost almost all the activation functions are being applied element-wise. So that means the GZ on a component of Z on a component of J is equal to G and apply on the Zi. So all these and the activation functions is being applied parallel. There are 3 commonly used activation functions in the middle layers. On the last layer, we can either use these activation functions, or we can use the softmax. But softmax is not element-wise an operation, so this will be slightly different. So for those like intermediate and the layers, and we can either using sigmoid as we mentioned, we can use hyperbolic tangent. That's also a very popular one. So you can see this hyperbolic tangents connect from -1 to 1, and we can have this ReLU functions as well. So the ReLU function is just maximum of the 0 and x. Okay, so we have and this is sigmoid. We have a hyperbolic tangent. We have like and the ReLU functions. Okay, so I don't want to talk about too much about theory of a deep neural network, but just let me give you some idea right here. So the neural network is called deep neural network if it has more than 2 layers, as otherwise it will be shallow. So basically right here, this will be a shallow neural network because we only have a 1 hidden layers, right? If we have a more than 1 hidden layer, it will be called as a deep neural network. So that means we have a multiple layer of hidden neurons, right? And each of that will be and the linear layers and followed by the element-wise nonlinear activations. So you can see the whole neural network thing is highly nonlinear is because we have this element-wise nonlinear activation functions, as I just showed right here. So these are highly nonlinear and combined with the linear and the linear layers. The parameter here is just for the weight and bias from the linear layers. We don't actually do any parameters training for that and for the activation function. So activation function is predefined here. Like 2-layer neural and a neural network, and we can use cross entropy loss in the softmax output. However, if you use a sigmoid output layers, then we have to switch back to the analog loss. Okay, so this is the common and the problems that you can think about this. We have an image and we want to distinguish cats and dogs. So basically my output layer will be 0 and 1s, right? So 0 is cats and 1 is dog. Then I'm going to reshape this image into gigantic columns and put this into my input layers. I'm going to have these 3 hidden layers, and we're going to tuning all these parameters for W1, W2, W3, B1, B2, B3. And you can change all these like number of neural and the number of hidden neurons right here. You cannot change the input layers neuron because that's coming from and the dimension of the input data, and you cannot change this output layers and the number of the output layers as well because it's all coming from how many labels that you want to make a prediction, which is the K. But you have a freedom to choose those hidden layers as well, and you can choose the number of the neurons in those hidden layers. All right, so but why the deep neural network will work? So there's something called the universal approximation theory. So basically it's, the whole idea is we are working with some classification problems, right? So the whole idea is we want to learn a decision functions, and to map any data into its correct labels. But this decision functions is really, really complicated. It applies a very, very high dimensional and points. So, however, the deep neural network actually can approximate this decision function f hat with arbitrary positions given sufficient depth that you need it. So this is guaranteed by universal approximation theory. So what does that says if and you can have any basically any functions from R big D to R. This D could be very large, and you can set some epsilon you need. And you can always find a deep dense, fully connected ReLU neural network that is the width is less equal to D plus 4, such that this function actually satisfy the following property and properties, i.e. the prediction of error of this neural network is very, very close to the ground truth of f hat. So the error is almost like less than epsilon. So, and you can choose arbitrary epsilon. So that's why you can reach arbitrary precision if you need it. I mean, it depends how much and how hard you want to train the problems. But of course, this is just give you a theoretical guidance that there exists such kind of network. But in general, that could be like way complicated to train that kind of problems. So we don't usually use this and idea in practice at all. And of course, in terms of computational side, training this like optimal like neural network is almost impossible because this loss function is highly non-convex. It is, it's almost impossible to find the like global minimums in this like situation. It's very likely, and you will be trapped in some local minimums somewhere. Okay. So this is basically introduction to neural network. And in the next lecture, we're going to talk about how we are going to train this W and the B's for given these models and for giving this loss functions. Once you are given these loss functions, hypothetically, we can use gradient descent method or stochastic gradient descent method to actually optimize for B and W. But obviously, this is a very complicated process. And what we're going to do is we're going to derive the math and basically derive the backward propagation formula, and at the end we're going to implement everything from scratch. Okay. All right. So that's it for today's lecture.